Hi, welcome to Why do physicists require 5 sigma for discovery, but only 2 sigma for exclusion? So, in this video, we're going to talk about how particle physicists decide whether or not some experimental data discovers or rules out new laws of nature that they're testing experimentally. As we'll see, the criteria for claiming a discovery are far more strict than those for ruling out some hypothetical idea. So in particle physics, we have the standard model, abbreviated SM. So the standard model is our current best model of particle interactions. Its predictions agree with the results of literally thousands of experiments to high precision. However, the standard model leaves a lot of questions unanswered. For example, it doesn't tell us what dark matter is. It also doesn't give us the origin of neutrino masses. And in the standard model, there are 3 families of quarks and leptons, but we don't know why. Also, although the standard model gives us a mechanism for generating particle masses, it doesn't tell us why those masses have the values that they have. The standard model also doesn't explain the baryon-antibaryon asymmetry of the universe, and it doesn't tell us what dark energy is. In fact, when we try to calculate the dark energy of the universe, we get an answer that is extremely wrong. This is known as the cosmological constant problem. And also, the standard model has the hierarchy problem. When we try to calculate the mass scale of the particles of the standard model, we also get a very wrong answer. Okay, so what do? We write down models of new physics, which I'll abbreviate NP. So if we have a model of new physics, usually it's built to address some question not answered by the standard model. This new physics model should be consistent with all measurements that have happened so far. This new physics model should also make testable predictions which differ from those of the SM. So then we can do experiments to test these new theoretical ideas. Now, sometimes experimental results disagree with the predictions of the standard model. This might indicate that there is some problem with the experiment. It also might be that the data displayed a large statistical fluctuation relative to its mean. Or it might mean that we've discovered new physics. Now, particle physics has very stringent criteria for deciding when an observation is sufficiently statistically significant to qualify as a discovery. We have the 5 sigma discovery convention. But what if there's no evidence in the experimental data for the new model? Then we want to see if the data can rule it out, if the data can exclude the new physics model. How strict are we when we're trying to exclude the NP hypothesis? Well, usually we're satisfied with ruling it out at something like 2 sigma. This is much less stringent than what we do in the case of discovery. Okay, so here we'll do the following. We'll briefly review the 5 sigma discovery convention. We'll discuss the 2 sigma exclusion convention. We'll discuss why we take different attitudes toward discovery and exclusion. And finally, we'll tie this behavior to Bayes' theorem. There is a bit of prerequisite information on this channel that you might find useful here. So we cover the 5 sigma convention for discovery in the video 5 sigma, the standard for discovery in particle physics. We're also going to be using Gaussian measurement uncertainties in this video. If you'd like to know more about those, you can watch the playlist entitled Mini Course on Error Bars, Measurements, and Decision Analysis. And also we'll be talking about hypothesis testing, so you might be interested in the hypothesis testing playlist. Okay, let's get started. Okay, so here we'll assume we're interested in a specific new physics model. Let's say that we're going to measure the rate of a certain process that takes place in the ATLAS and CMS detectors at the Large Hadron Collider at CERN. Let's call this rate R. For example, when the LHC experiments discovered the Higgs boson, they looked for pairs of photons which formed a certain invariant mass. But other processes also produce photons. So they looked for an excess of these photon pairs compared to what would be made by other non-Higgs processes. Now, before we do the experiment, let's plot a quantity that we're going to call P of R measured. So this is the probability distribution of the measured value R measured that we will get out of the experiment. We're going to plot this for our null and alternative hypotheses. Now we're going to take the measurement errors as Gaussian with an uncertainty that we're going to call sigma R. R measured will be Gaussian distributed around the true value of R true, with a standard deviation of sigma R. Okay. So under the standard model, R takes the value RSM. So our null hypothesis is that the true value of R equals RSM. Under our new physics model, R takes the value RNP. So our alternative hypothesis is going to be that the true value of R equals RNP. So here in the plot, we've labeled RSM with the blue arrow and RNP with the red arrow. Okay, so under the null hypothesis, R measured will be Gaussian distributed around RSM. And under the alternative hypothesis, R measured will be Gaussian distributed around RNP. And here note that on the x-axis we've plotted R measured in units of sigma R. Okay, so now we're going to do the actual experiment. We're going to measure R, and we're going to actually get R measured. If the value of R measured falls within, say, 2 sigma R of the value of R predicted by one of the hypotheses, we would consider the measured value R measured to be compatible with that hypothesis. So here we show a measurement that would be considered compatible with the standard model, with the null hypothesis, but not compatible with the new physics model, the alternative hypothesis. So here R measured has fallen within 2 sigma R of the value RSM, but it has not fallen within 2 sigma R of RNP. Here we show a measurement that would be considered compatible with the new physics alternative hypothesis, but not with the standard model null hypothesis. You can see that here R measured has fallen far from RSM, but within the bar of 2 sigma R around R new physics. And finally, here is an example of a measurement that would be considered compatible with both hypotheses. So here, R measured has fallen right in between the values of RSM and RNP, and it's within 2 sigma r of each of them. Okay, so with that, let's first look at the criteria for discovery. Okay, so here let's take a scenario where the null and alternative hypotheses are very well separated. So here RNP minus RSM is equal to 6 times sigma r, so 6 times the standard deviation of either of these two Gaussians. Now let's say we do the experiment and R measured falls 5.2 sigma r above RSM, the null hypothesis standard model expectation. And also, let's say that this result is compatible with RNP, the new physics expectation. This is more than 5 times sigma r above the standard model prediction, so it fulfills the 5 sigma convention. Now, if the null hypothesis is indeed correct, so this means that the standard model is the correct model of nature, and our uncertainties are understood, so we have the width of the Gaussians in this plot correct, then the probability that the result R measured would fall above RSM plus 5 sigma r is less than 3 times 10 to the minus 7. The rest of the time it would fall below this somewhere in the area shaded in blue. Now this is a very rare result under the null hypothesis. The 5 sigma criterion is a statement about how poorly the measured result agrees with the null hypothesis. Okay, now let's go on to the criteria for exclusion. Okay, so here in this example, the standard model and new physics predictions, RSM and RNP, are only 3 sigma r apart. Let's say that R measured falls 2.2 sigma r below the new physics expectation RNP. This result is very compatible with the standard model hypothesis. Now, this result falls more than 2 sigma r below RNP. Under the 2 sigma exclusion convention, this measurement would rule out this particular new physics model. If the alternative hypothesis was correct, so the new physics model is the correct model of nature, and again we understand our uncertainties, about 2.3% of experimental results would incorrectly rule out the new physics hypothesis under the 2 sigma exclusion convention. So the 2 sigma exclusion convention is a statement about how well the observed result agrees with the new physics hypothesis. But this is much less stringent than the 5 sigma discovery convention. Now, we should briefly mention that there are other conventions for discovery and exclusion. And in particular, one common exclusion convention is the 95% confidence level. So under this convention, if the alternative hypothesis is correct, 5% of experimental results would incorrectly exclude it, unlike 2.3% that we saw under the 2 sigma convention. For our example, this corresponds to R measured falling less than RNP minus 1.64 sigma r instead of RNP minus 2 sigma r. Okay, so now let's ask the question, why do we use such different criteria for discovery and exclusion? The answer is that before we conduct our experiment, we assign a very small a priori probability to the new physics hypothesis. This is motivated by the fact that the standard model is a well-tested theory, while the new physics hypothesis is highly speculative. And even if the standard model is incorrect, what is the probability that this particular new physics model is the correct model of nature? Okay, so basically before doing the experiment, we assign a prior to each of these hypotheses. So we're going to write P of NP as the prior probability that the new physics model is correct, and we're going to call P of SM the prior probability that the standard model is correct. And here we'll ignore the possibility that neither of them is correct, despite the fact that that's probably the most reasonable hypothesis. So our starting assumption, which we don't make formal but is what we do in our heads, is to say that the probability of the new physics hypothesis being correct, PNP, is much, much less than 1. And the probability that the standard model is correct, which is 1 minus PNP, we take very close to 1. Okay, so now let's think about the discovery scenario. So because we take the new physics to be extremely unlikely before the experiment takes place, so we're taking the probability of the new physics to be much, much less than 1, then the observed result must, 1, be reasonably probable in the new physics hypothesis, and 2, be extremely improbable in the standard model hypothesis, in order for us to take the new physics hypothesis seriously based on the experimental result. Basically, we need extraordinary evidence that the standard model hypothesis is incorrect in order to believe the new physics hypothesis. This is why we have the 5 sigma convention. Now let's think about the exclusion scenario. So as the new physics hypothesis is taken to be extremely unlikely before the experimental result is obtained, we need much less stringent evidence against it, say 2 sigma, in order to reject it. So what we're doing in situations like this is actually an informal example of Bayesian reasoning. So Bayesian reasoning is probabilistic reasoning based on Bayes' theorem, which is shown here. Now we won't go through any of the math, but using Bayes' theorem, you can take your prior probabilities for the new physics and standard model hypotheses and your experimental results and come up with new probabilities for the new physics and standard model hypotheses given your priors and the result of your experiment. If you'd like more information on Bayes' theorem, you can check out the Bayesian playlist on this channel. Okay, so let's briefly summarize. Here we've discussed the 5 sigma discovery and 2 sigma exclusion conventions in particle physics. We saw that the 5 sigma discovery convention is much more stringent than the 2 sigma exclusion convention. We also discussed how this follows from prior probabilities that we apply to the standard model and new physics hypotheses, and briefly, informally related it to Bayes' theorem.